I did some analysis, both of further analysis since you and I talked of LLVM and WASM, and the problem with both of them that ultimately made me feel less happy with them was that the concurrency story is non-existent. So we introduce all this concurrency at the top, and then it all gets evaporated to a kind of interleaving down at the bottom, which doesn't actually take into account the support at the hardware level for the concurrency. And it's not clear at the end of the day how long it will be before those things are rectified. So again, these are kind of trade-offs. It's not none of, because WASM is a moving target, and even LLVM, even though it's much more stable, is a moving target. It's much harder to give definitive or cut and dried statements about either of them. But it seemed to me that having this concurrency facade closer to the metal would be the right way to go in the long run. And also, there's some other considerations that have been driving me. One is essentially, I feel like we need to have a lot more control and ownership of the code. So, for example, in the compile path, I don't know if Jack, if you remember, the compile path that we had been considering was from the RoVM intermediate representation to Zinc via Lambda with the limited continuations, and then Zinc. Zinc is the fast version of the OCaml virtual machine.
Oh, okay, right.
And Zinc has been formally verified, and the Zinc to LLVM has been formally verified. So the point was that we would get some of the formal verification a lot sooner that way, and so there are some trade-offs. The path that I'm investigating now, that I'm leaning towards, would we would pick up a proof obligation for the VM target that I'm proposing. So that would have to be formally verified. Because I worked on the machine myself, I'm not anticipating that verification process to be particularly onerous, and it would be a way to exercise the K framework. So that would be as another one of another sort of proof point on the utilization of the K framework. So without much more, I'll show you the VM. So I'll do a quick.
Can I just ask one thing first? Have you thought about using, like, for example, Erlang's VM instead of LLVM or WASM? Because that seems to have quite a lot when it comes to concurrency.
Yeah, that's an interesting one. The thing with Erlang's VM is that it's a little less. How do I say it? It's a little less regular. It was kind of organically grown, right? And it kind of developed in one direction, then another, and then another over the course of Erlang. And so providing a clear-cut compilation from the RoVM would be more challenging. Not impossible, but certainly more challenging. But the proof obligation would be the one that would be even more difficult. With the Rosette VM, we worked pretty extensively with Gul Aga. And so we had a pretty clear sense of what the formal model was, even though we didn't provide a, and it's very uniform. I mean, it's not like a hodgepodge. It's extremely uniform.
Right.
So that makes the proof a little simpler. And then when, I'm not going to claim by any stretch of the imagination that Rosette has the same level of industrial exposure or pressure that Erlang did, but Rosette had quite a bit. So in particular, we used it to build an ATM network management system for Sumitomo and TSB banks. We used it to build a data cleaning application for Belcore, and other things like that. So it doesn't have nearly the same level of exposure that Erlang did. But I'm quite confident that the machine design itself, as opposed to any particular implementation, is at least as robust, if not more so.
Right.
So, and here, what we really need is, we need the machine design, probably more than we need the existing implementation. And as I spoke with Henry Till, do you remember Henry, Jack?
Yeah, absolutely.
Yeah, I spoke with Henry Till and and Gary, and the thought was to do a kind of clean room re-implementation. So if it's done in Scala, the trade-off is we lose some of the performance. The Rosette, the C++ implementation of the Rosette VM does a lot of tricks with memory, so that the instruction pointers and other things are all byte aligned. So you can do pointer arithmetic tricks to get pretty good performance. At the time, so this was in the mid 80s. The Rosette VM was 1/4 of the speed of C, which was just unheard of, right? It was like, wow, for a managed code solution, that's amazing, right?
Yeah.
In today's environment, it would, just completely scream.
Yeah.
So, so there is that trade-off as well. So let me just do a quick little demo. I'll start from scratch. All right. So what I've to demonstrate the working of a virtual machine, you need to be able to provide the virtual machine instructions. And one of the easiest ways to provide the virtual machine instructions is to provide it via a programming language. So I'm providing it via the Rosette programming language, which in some ways can be thought of as the beginning of my journey into concurrency at the level and scope that we I've been involved. Rosette was untyped. Essentially, it was a realization of Hewitt's idea of actors. It's often said that Scheme was Sussman and Steele taking Hewitt's actor ideas and simplifying it down to just a single-threaded idea. So with Christine Tomlinson and Mark Scavell and Greg Lavender and others, the thought was that we would provide a manifestation or realization of the full idea. Rosette, so the actor model here is fully reflective. So you can kind of think of it as like the untyped version of Rolang in some ways. It's not quite like that because actors have a principal port limitation, meaning a concurrent process has only one place to interact with it, whereas we know with Roland contracts, there are multiple channels that a process can be listening on. And it was actually this that was one of the main reasons why I shifted towards pi calculus-based models, was because the principal port limitation is a significant limitation when you're talking about real-world design patterns. Human decision-making processes often involve multiple channels, listening on multiple channels. You can actually see it in individual humans. I remember one time I was sitting on my motorcycle at a red light, and the next thing I knew, I was both simultaneously revving the accelerator and holding the brake as hard as I can, gripping the brake as hard as I can. The light was green and someone was running a red light. So different parts of my brain were responding to different inputs across different ports. And they were responding independently, and they weren't actually perfectly synchronized. So you can see this kind of stuff even in the human brain, but it certainly happens a lot in human decision-making processes. So without further ado, let's just write a little bit of code in Rosette, and I have prepared a little bit of code here. Here's a continuation passing factorial, and I'll walk through that in just a second. All right, so and I'm defining it and then applying it all in one expression. And so I'm providing the argument 3. So here's the continuation passing. I've used, rather than use the actor model, I'm using something that's mostly living inside the functional subset of Rosette. Even though everything is under the cover is concurrent, what happens here is that it's the synchronization constraints are forcing everything to be single-threaded because of the way I've written the code. So essentially, it's just exactly as you expect. We're saying that the identifier fact. I don't know if that. There we go. That might be a little easier to read. The identifier fact is bound to something that's called a proc. A proc takes 2 arguments, an n and a k. Here, n is clearly going to be some kind of numeric because we're comparing it to see if it's checking to see if it's less than 1. In the case that it is, we apply k. So apparently k is some kind of lambda term or functional term, and we apply the k, which is a continuation, to 1. Otherwise, we call we invoke whatever is bound, i.e. the proc that's bound to fact, onto the decrement by 1 of n, and a new continuation where the continuation is like a lambda term. It's a single-threaded computation, which is going to take an input n, multiply that input by take an input x into the computation, multiply that input by n, and then apply the continuation that we receive to that, right? So that's effectively a continuation passing style factorial. And then we apply the proc that is bound to the identifier fact to 3 and the identity continuation. And so if we look at this expression, we expect that to come back as 6, and in fact it does. Let's run it on something a little larger than 3. How about 4? That works. That seems to be the right answer. How about 5? That seems to be the right answer. So there, that's
an example. You pass it some other more complicated continuation instead of the identity.
Oh, yeah, sure. So we could supply something like display here I am, bang, and then return x. And then in order to do that, we have to do a seek, which is that we have to say the order in which these two are running, and this is the result of the seek block, the last one. So in the style of prog in Lisp, that's what's going on. So we see there it is. It's displaying. Oh, let me do that with slightly prettier. There. So clearly, that's the end. That's the end of the chain of continuations that we're building up. If we want to see a sequence of them, we can do display. I am here too. And we see that builds up the chain of continuations. And this is the final one. So you can see these are effectively the points in the stack, right? And there's the top, the end of the stack of continuations. And there's the answer. Okay, so now moving on, this is not so much about learning how to program Rosette, more it's about investigating the Rosette virtual machine. So let's go and look at what this code looks like when we compile it. So essentially the compilation provides, as is fairly standard for these sorts of things, a literal vec, a vector of literals that's associated with the code, and the actual code vec. The code vec is consisting of several different opcodes, for example, allocating and providing args, stuffing literals into args, and creating procs, right? Allocating procs, and ultimately delivering results to some awaiting thread or continuation. So that's there's the compilation and sort of a taste of the instruction set. Now, rather than go through all of this in detail, let's simplify the discussion even further and just look at the concurrency model here. So essentially the concurrency model is message passing, and the only form of real concurrency at the level of the VM is message arrival order non-determinism. So let's see what that means. What it means is we have a distinction between an expression like this and an expression like this. So what this really is a synchronous send of the message plus to the actor 1 with the additional arguments 2, and wait for the result. And when we get the result, hand it to the outstanding continuation, which is this REPL. That's the actual meaning of this expression. Whereas the meaning of this expression is asynchronously send the message plus to the actor 1 with the additional arguments 2, and don't wait around for the results. So if we do a compilation, we should see that reflected in the bytecodes. So here is the compilation, and here is the allocation required for the literals. Here's the loading of the literals. Here's the making the arguments available to the plus, and here is the transmission of the results to the outstanding continuation. By comparison, we have actually 2 threads. So this thread here is the asynchronous send. Since the asynchronous send doesn't ever return a result, the only thing that we need to do is to load the no intrinsic value literal in return. That's all that happens on that thread, because that's the entire meaning of the send expression. On another thread, what we do is run exactly this code here. And since there is no, but notice that instead of returning it to the outstanding continuation, the final call is the send. So that's the difference between the two, and that's why it's the interaction here, which is why we don't see sort of between this thread and this thread, why we don't see anything happening when we call send 1 + 2. Nothing is displayed at the prompt. So now let's take a look at an alternative, which is to display results. So notice the difference between that expression and that expression. So here we see the 3 and the printer, whereas here we see just the 3. And that's because the result of a display, of any display, is the printer object. And then it also side effects the world by printing to the console whatever it was told to print to the console. In this case, it was told to print the results of 1 + 2, which is 3. So that happened to the console, and then the REPL printed out the result of a display expression, which is always the printer. So if we then compile that, there we are. So we see that this is somewhat different, right? Because now we have the display as a part of the computation, right? So this is transmitted, and then this is transmitted. And this is, in fact, the result, which is the printer object. Now, if we compare that with one other possibility, which is the send display, what would we expect to happen? What we expect to happen is the send expression returns nothing, but the display side effects the world. So, and the thread, the result of the thread that is associated with the display should return the printer object. But because that thread is not connected to the REPL, we should never see the printer object, but we should see the side effect of the sending something to the console. So that's our expectations for this expression, and that's exactly what happens. And now if we compile that, let's see what happens. And it's exactly as we expected. So if we compare this with this chunk from 2 to 13, the principal difference is transmitting it to the outstanding continuation versus the send instruction, right? And then this thread here is as it was in the send plus of 1, send plus to 1 with 2. So this thread returns immediately. There's nothing in a thread. There's nothing in a send expression other than no intrinsic value. It's like the equivalent of, I don't know, set Q in Lisps. So that gives us an overview of the VM. We can go into the bytecodes. Now, what has to happen with this VM is to extend it, or what would make it, how do I say, more suitable or more convenient, I guess, for for the crypto space is to add some cryptographic opcodes that will make it easier, as has been done with, for example, the EVM. But here we're not starting from scratch. We're starting with a VM that's been tested in industry and that we have complete control over. In some sense, like the way I like to think about this is by comparison to Gavin Wood's yellow paper. So where Ethereum, essentially began from, here's a spec on paper. We are beginning from essentially this is the spec for the yellow paper. It's C++ code that's been tested under load for numerous applications. And here is effectively the executable semantics for the transition for the virtual machine. So we have in the method execute for the virtual machine, we have essentially the what happens with each kind of instruction or each kind of opcode. So this gives us not only an exhaustive list of the opcodes, and we can get those from the other declarations, but it says what you do with respect to them. So this is like the transition steps in the specification, the yellow paper, or the transition steps in the Java VM spec or what have you. So this is, and you can see it's actually not very big. It's quite tractable for one or two people to understand it. And the proposal then is to do a clean room reimplementation, as we've seen with other implementations of the yellow paper. So that's kind of the thought. It's a little bit off topic specifically from Casper, but this is the framework into which we will be insinuating Casper and actually utilizing Casper as well. So in particular, we think of Casper as storing the state of this virtual machine, and the idea is that we effect a correct by construction compiler down to this level. We'll have to verify two steps. We'll have to verify by hand the compilation. So essentially what we have to do is to formalize this semantics, which is not very hard. And then we have to, because in some sense we already have a formal semantics. And we have to prove that semantics is correct, and then we have to formalize the compilation from the Rolang VM intermediate representation code down to this code. Now, the nice thing is that Rosette does have the notion of first-class continuations. So if you look at and those are expressly represented in the VM. So it's essentially very, very much like a version of the delimited continuations machine in the paper that you and I were working off, Jack. So that's the key idea, or that's what accelerates this process greatly. So that's the thought, and that's kind of the end of my little spiel here. Who else showed up? I noticed that someone else showed up. Oh, that was Casey. Cool. Hi, Casey.
Hey, Greg.
How's it going, man?
Pretty good.
Cool. Did you show up in time to see the byte code being generated?
No, I showed up right when you were walking through the C++ code.
Okay, cool. here, I'll show you some of that real quick.
Okay.
So essentially, here you can see the bytecode of a continuation passing style factorial. And then I was going through the different bytecodes that are associated with synchronous send and receive and return versus asynchronous send, which shows up here and then here, and then comparing that to operations that side affect the world. So there and there. So I've been talking for a long time. I want to get other people a chance to talk. Otherwise, I will move over to the discussion that Vlad and I have been having about the deduction system for the safety calculation. All right. All right, so let me bring this up. I think this is it. Yeah, okay, cool. So I spoke about this last two times ago, I think. So let me just, since it's been a couple of weeks, let me just refresh the context a little bit, and then I will dive into the deduction system and why that's a reasonable approach. So the context is that, you know, Vlad and I have been looking at a way to classify all the different kinds of faults. This is largely driven by Vlad's investigation, and all I did was to write down what I heard him say, so that we could, you know, make sense of it and see if it was reasonable or rational. And then the second part of that was Vlad was running into some complexity issues. So essentially what he was finding was that he would reduce even the lower bound computation of the safety calculation to knapsack, which has sort of challenging complexity, let's say. And so the thought was to utilize some of the tricks that we know about in this setting to improve the complexity. And then it turns out, lo and behold, that fits nicely into the fault model. So just very, very quickly, the fault, we think of a network of validators. Since we have ins being used all over the place, I subscript it with V as essentially a big parallel composition of processes, validators, that are running in some context. And that's in parallel with essentially a communications network, right? So then what I just said was, we have some process, parametric in a vector of names N and a vector of names V. So N will be the means by which N is largely associated with the network, and V is largely associated with the validators. So that network is decomposed into two subpieces. So that's what the vertical bar is. So it's a bunch of validators that are sitting inside some execution context and the network itself. Now, the communications network is the channel, or, you know, you can think of this as like, you know, TCP/IP, right? So it's a lower in the stack, and the validators are sending and receiving messages through the communications network. The context that the validators are running in, and this is the interesting bit, right? So if in the communications network is communicating via N, and the validators are communicating via V, how do they ever talk to each other? Well, the communications context in which the validators are running is a set of gates. All right, so the gates act as the bridge between the V's and the network, right? And essentially what they do is they simulate deciding when messages get through, so you can simulate network faults. And they also simulate Byzantine behavior, or at least some portion of Byzantine behavior. So you can isolate and localize most of the weirdo behavior inside these gates. So from an attack point of view, you can think of the gates as representing the place where an adversary can insert themselves. And from a defense point of view, you can think of the gates as prophylactics against attacks. So for example, gates could represent adding reliable messaging to the communications network. So exactly once in order, durable message delivery would be an example of something that you could add as a prophylactic. Just to make that clear in a picture, what we're saying is if validator V1 is talking to validator V2, that really looks like this, right? So validator V1 talks to its gate, and that gate then uses int to talk through the network to other gates, which are then forwarding messages on or proxying messages to the validators. That was the basic setup that Vlad used to characterize or classify faults. Now what we can see is that if we relate that to the kinds of validator strategies, then we see a strategy is expressed, for example, here as a pi calculus process. I've written it for readability in Rolang style, but you could easily write this in pi calculus form. And essentially, you know, an innocent strategy works more or less like a function that's plunked down in, more or less like in Rosette, where the function is potentially receiving across some number of channels. Hence my problem with a principal port model in the actor model, is receiving across some number of channels, say VI, and what it's receiving are bets. So we've talked about several times in the Casper stand-ups the structure of bets, but essentially they have, and what's common between Vlad's model of bets and my model of bets is they have at least a sender, they have at least an estimate, which is the value that everyone is trying to consensus over, and they have a justification that supports why this estimate is good and why it's reasonable to send this bet at this point in the protocol. So you can think of the justifications as essentially trees of bets. So a bet itself is always a tree. So an innocent strategy is listening over some channels for bets and then checking to see if those bets match certain specs. And when they do match certain specs, they are calculating new estimates based upon the bets that they have received, and broadcasting them out to the rest of the validators with this bet that they have received as extending their justification. So that's the shape of an innocent strategy that would be operating at one of these V nodes. Okay, hopefully that makes sense. Any questions so far? Awesome. Silence is golden. Okay, so we've talked about how this view allows you to talk about both attacks and defense. And then Vlad has a wish that equivocation can be modeled as copies of innocent strategies running in parallel with a gate selectively switching amongst them. So it would be nice if all Byzantine behavior could be characterized thusly. We have no such formal proof, although I could see how you might code it up. Essentially, these things become storage for various versions of the world that the gate itself is considering. Okay, I don't remember the point of this, but Now let's talk about the safety calculation itself in this context. So the safety calculation is going to be thought of as taking place in a fault context. What kinds of faults? Well, we just went over that. So this is the sense in which we are talking about faults. For now, we simplify the faults down to just two things. One is part of it is whether or not a particular validator sees another validator as acting in a Byzantine manner. And then there's a record of the weight associated, sorry, the weight associated with that validator. So a fault context in that sense is essentially just a map from addresses representing validators to a pair, weight, and a judgment about whether or not they are Byzantine or innocent. Okay, and additionally, a safety judgment utilizes the notion of a view. So what is a view? A view is nothing more than a set of bets. So there are two possibilities. Either you can extensionally provide the set of bets, or you can provide them intentionally in terms of a program or a formula. Here we are utilizing formulae to intentionally describe bets. And how do we do that? Well, I utilize the ladle algorithm, this developed by Mike Stay and myself, to generate a set of formulae directly from the notion of bet, right? And that's what this specifies. So at the top level, a history or a set of bets is either the set of all bets, or the complement of the set of bets, or the intersection of the set of bets, or a bet spec, which specifies bets in terms of their shape. So a shape is a triple consisting of a sender spec, an estimate spec, and a justification spec. And then surprisingly or amazingly, the sender spec looks remarkably like this, and the estimate spec looks remarkably like this, and the judgment spec looks remarkably like this, with the extra added stuff that because there's interior structure on the trees, we can take advantage of that. So then what is a safety judgment? A safety judgment is an expression like this that says this context thinks that this view judges that this estimate spec is safe. So given this information about the fault context, we can, and this view, or this set of bets that we've seen so far, then we can judge that bets in this, estimates in this spec are safe. So now that we have the shape of judgments, we have to say what the rules are in the deduction system. So what are the rules? Well, we need two kinds of rules. One are the axioms, which are true. These are judgments that are true without any additional assumptions. And then we have inference rules, which are judgments that are true given some assumptions, and the assumptions are the results of having run previous inference rules, which we know to be valid. Okay, so essentially this system is a recursive specification starting from some ground cases, which are the axioms, and some recursive steps, which are the inference rules. So here, the principal axiom that we want to focus on is that under no assumptions about the innocence or Byzantine behavior of the validators, if all the validators all publish the estimate B with no justification, then B is safe. If magically they all agree, then they all agree. That's the axiom. And now what we have to do is to discuss the inference rule for what is the inference rule. So the principal inference rule of this system is that we want to, and I've written it down here in a slightly different way. What we want to ask, I think I put it in English here. We want to ask when it is reasonable for a single validator to change its estimate. When is it reasonable for a validator to change its mind based upon its information? So again, Vlad and I are arguing about this, but here's my proposal, and you guys can think it through for yourselves. So it is safe for a validator to change its mind if in the fault and this has to do with updates to its fault context and its view. So we're saying under what conditions can we update the fault context and the view so that it is safe for the validator to change its mind. When we discover that, then we have the essentially the minimal information required to say that the validator is acting in good conscience when it publishes some bet, which will then be used as an update to a view for another validator. Vlad's work, as I understand it, is largely focused on the other side, not on the publication side, but on the recipient side. So essentially, there are two dimensions here. There's producer and consumer of bets, and then there's the information inside a particular view so far. And if you don't take into account the intentional information, let me find that here, the intentional information associated both with the updates to the view, or the calculation of a new bet from an existing view and a new information, and the producer consumer side of this, then the complexity goes through the roof. So what we're doing is adding additional intentional information to tame the complexity. So what we say is, if it is the case that the combined weights of a Byzantine-free subset of validators all think that an estimate that is outside of the current validator's estimate spec is safe, then it is reasonable for the validator to update its mind, change its mind, and update its safety spec or its estimate spec to say that that estimate is safe. In other words, if a bunch of people, all of whom the validator respects, say that where respect is calculated by stake, say that this estimate is safe, and that weight is greater than the weight of the current validator, then it is safe for the validator to update its estimate spec. So that's the basic inference rule. And again, I've rephrased it here in functional style to show the relationship between the deduction system like this, with the inference rules like this, and how it might be realized, say, in a functional language like Scala or something else.
Hey, Greg, can you hear me?
Yeah.
Hey, sorry, I didn't interrupt earlier because you were explaining stuff, but I had a comment about that last inference rule.
Yeah, go for it.
Why would you make it based only on the that the validator has to see, weights greater than himself rather than weights greater than the current evidence he has? Like a validator with epsilon weight can be trivially caused to change their mind if people with more weight than him say something otherwise.
That's correct, and that's an alternative inference rule formulation, and I'm open here. I think that's a reasonable alternative, and one that I have been exploring.
Okay.
Yeah, no, those are absolutely, and you get different inference systems that way. Yeah, absolutely. So then now the point is how to relate all of this to the types and the intentional information that we capture in the statements of the strategies. So what we will do is we extend the safety judgments to a type judgment about the safety of a strategy. And so here, what we do is we now embed a validator's strategy into the judgment. So here we had judgments like this, and now we're going to add to that mix a statement about the strategy. And essentially it says that if the validator does think that an estimate is safe, then eventually it is possible for them to produce that estimate, right? This is the kind of type judgment that we utilize to connect this kind of intentional information with this kind of intentional information, and then build up, a correct by construction Casper. So hopefully that's making sense now. So again, what are the goals? So the goals are to write down a clear spec for the safety calculation, and to tame the complexity of the safety calculation. So the first thing to do then, from my point of view, is to provide a compositional account of the safety calculation. That's exactly what this does. We have a bunch of, to use technical language, recursive domain equations, and therefore they are clearly compositional. And those recursive domain equations are related to recursive calculations over the domain equations. So we've introduced compositionality. That's the first way to tame complexity. The second way to tame complexity is to introduce intentional information. This is often considered to, counterintuitive. It can be counterintuitive to think that you might reduce complexity by adding information. But if you think about the famous game, Name That Tune, if I sing you one note, you have lots and lots of tunes that could be. If I sing 3, 4, 5 notes, suddenly you have oh my gosh, it's snowing. It's awesome. But my son and I were just talking. He was saying he didn't think we'd get snow this year. Yeah. So anyway, so the point is, in the Name That Tune game, adding information reduces the complexity of the task. And that's what we're doing here. We're adding information, and in particular, we're adding information about strategies and their relationship to the safety calculation. So this doesn't always work in the wild, right? So like part of the debate or dialogue or discussion between Vlad and I is, how do you know that this is the code that a validator is running, right? And so there's lots of different angles on that conversation, and I'm happy to have those, but it's 8:01 and I'm on a super tight time schedule today. So I'd be happy to, field conversation about this in the, in Skype and all the other channels, or, later this week, even if people want to hear about it. Yeah.
Are these slides available somewhere?
I can make them available. I think I put them in the channels some time ago in preparation for today's talk, but I can republish them.
Cool. Thanks a lot, Greg.
Yeah, thank you.
I was wondering something about the Rosette VM.
Yeah, of course.
You got.
Yeah, just I got a minute. Yeah.
Okay. Well, 1 minute. Just what's the relation between the Rosette VM and the Ro VM that was mentioned in the scenario architecture document?
Yeah, I went over that at the top of this talk. You didn't get. I'll just describe it briefly. So the thought has always been that essentially we bubble away the so you can see my hands, nothing up my sleeve. We bubble away the Row VM in terms of a staged compiler pipeline. So, which is correct by construction. So the Row VM spec is there principally to judge whether or not each stage in the compiler pipeline is correct. It doesn't execute, although you could execute a bytecode interpreter for it. Instead, you have a path to the metal by a series of steps that reduce you take the bytecode for the Row VM that is directly related to the calculus, and you transform that into new bytecode, and then you transform that into new bytecode, and through a series of steps you get to bytecode or machine instructions. So either bytecode you know how to run in terms of the metal, or you have machine instructions. And this way you have a correct by construction and formally verified path all the way to the metal. So the proposal was to factor this down to LLVM through zinc. So that was one proposal on the table, and there are lots of advantages for doing that. However, looking at that very carefully, and actually in terms of the zinc code and the LLVM code and other things, when you begin to reduce that proposal to brass tacks, the biggest problem that I see, there are a number of problems, but the biggest problem that I see with that proposal is that LLVM's concurrency story at the end of the chain is a mess. Okay, so there's no good documentation. I can't get a straight answer on a number of things. And so I would be reduced to writing little code experiments to figure out what it actually does. And that's just too risky. So the alternative is to so there are a couple of alternatives. One is you essentially just get interleaving as a part of the compiler, and the bottom is a sequential machine, which is just, to me, insane, because underneath that view are all these multi-core chips that you're throwing away.
But the Rosette VM is not a sequential machine.
Correct. So thank you. So now returning, so popping the stack. Of our discussion. So instead of using the LLVM, we consider a different compilation target, one that is closer to our view. So again, the importance is to have a comparison between the two. So the steps were, we go from the Row VM to essentially a lambda calculus with delimited continuations. So the delimited continuations are representing the threading. And then you go from that down to, via the zinc virtual machine for OCaml, down to LLVM. So each of those steps has been formally verified by third parties. The downstream steps, not the Row VM to delimited continuation, but I can produce that. That's actually quite straightforward. It's very simple. So instead, what we say is we're going to collapse that end of the chain down to a virtual machine that already has first-class continuations and concurrency, and whose spec is small enough that if it isn't already formally proved, taking on the proof obligation is not onerous. Right? So the trade-off is existing path with formal proofs versus shorter path, better matched from the source to the target, and we pick up a proof obligation. That's the trade-off. Plus, do I know the code? So I will personally have to come up to speed on portions of LLVM that are not clear, and as I said, are not documented well, or in a manner that I can clearly understand them. Whereas since I was involved in the writing of the the Rosette VM, I know the code inside and out. I have access to the source code. In fact, we with Henry Till involved, we just got it compiling. It's an older code base for 32 base machines, and we got it compiling for the 64-bit, which is what I demonstrated at the top of the hour. So with that, I really have to go. Are there any burning questions there? Did that make sense, Casey?
I'm still lost. If the plan is to still target LLVM or not to, and to use Rosette instead.
Right. So again, I kind of said that at the top of the hour. So the plan to date is to take the existing Rosette VM implementation and treat it as the equivalent of an executable spec. It would be like Gavin Woods, instead of handing you the yellow paper, he handed you an executable spec. So I made this point earlier. If we go here, here is the equivalent of the information in the yellow paper, except it runs, right? So right. So that's the difference. And the point is that we would do a clean room reimplementation using Scala of that VM. And that's the proposal to date, because that gets us to market much faster with a VM that I know the ins and outs of.
Oh. Well, why did you ever want to target LLVM in the first place if Rosette was always available?
So as I mentioned before, this has to do with wanting to do correct by construction as far to the metal as possible, right?
Okay.
Yeah, right. So again, the aim here is to be able to present automated proofs for all pieces of the system, end to end, so that anyone skilled in the art can relate the executing code to the spec in a way that they can verify for themselves that it is correct, right? So the point is that with checksums and other kind of assurances about chain of custody, you can be completely trustless about the relationship of the compiler and the virtual machine, and not be worried about injection attacks and bytecode and that kind of thing.
Sure.
That makes sense?
Yeah, thanks.
Sure. All right, I gotta jump off. Talk to you guys later.